All right, let's dive into one of the coolest tools in data science, clustering. It's all about taking what looks like a total mess of data and finding the secret groups, the hidden patterns that are just waiting to tell us a story. It's going to be fun. So, let me start with a question for you. Think about this for a second. You've got marketing teams trying to find customer groups, banks trying to spot credit card fraud, and investors trying to build a solid portfolio. I mean, these things sound completely different, right? But what's the one thing they all share? Well, the answer is that they all, at their core, need to find hidden groups within their data. And the technique they use is clustering. This is a huge idea in what we call unsupervised learning. And all that means is that we don't go in with any answers already in mind. We just let the data itself show us its own natural structure. We let it speak for itself. Now, to bring this down to earth, let's imagine a real-world problem. We've got a retail company, and things aren't going great. Fewer people are clicking on their ads, and they're losing loyal customers. Their one-size-fits-all approach just isn't cutting it. What they want is to see engagement shoot up and have fewer customers leaving. And clustering, that's the bridge that's going to get them from here to there. So where do we even begin with grouping things? Well, it all boils down to a really basic human question. How similar are these things? That's it. We need a way to look at two customers or two transactions and ask, how close are you really? Things that are close get grouped together, and things that are far apart don't. To put some real numbers behind that idea of closeness, we need something called a distance metric. You can just think of it as a ruler. It's a mathematical rule that takes any 2 points from our data and just spits out a single positive number that tells us exactly how far apart they are. This is the bedrock of pretty much every clustering algorithm out there. And what's cool is that there are different ways to measure distance. One of the easiest to picture is the Manhattan distance. Seriously, imagine you're a taxi driver in a city like New York. You can't just fly over buildings in a straight line, right? You have to drive along the grid, block by block. That's the Manhattan distance. But the one you're probably most familiar with from, high school math is Euclidean distance. This is that simple, straight-line path between 2 points. As the crow flies. No city blocks in the way, just the shortest possible line. And honestly, this is the one we use most of the time for clustering. All right, so we've got our rulers, we know how to measure distance. Now, how do we actually make the groups? Well, there are a ton of ways, but one of the most famous and easiest to understand is an algorithm called k-means. The name actually tells you everything you need to know. The K just stands for the number of clusters you want to find. You have to tell it that up front. And means, that refers to how it finds the center of each cluster. It calculates the average, or the mean, of all the points that belong to that cluster. That center point is called a centroid. So how does it work? It's kind of like a little dance that it repeats until it gets it right. First, it just randomly drops K centroids onto our data. Then, for every single data point, it asks, which centroid are you closest to, and assigns it to that group. Then, the important part, it moves each centroid to the new center of its group. And it just does that again and again and again until the centroids stop moving around. Okay, this leads us to the big multi-million-dollar question when you're using k-means. We have to tell it the number of clusters, k, to look for. But how in the world do we know the right number? If we pick a k that's too small, we might be squishing different groups together. Too big, and we'll be splitting natural groups into tiny little pieces. So what makes a good set of clusters? Well, we're really looking for two things. First, we want the clusters to be tight. That means all the points inside a single cluster are really close to each other. Second, we want them to be well separated. That means the different clusters are far away from each other. The goal is to find that perfect K that gives us the best of both worlds. Thankfully, we're not just guessing in the dark here. We've got a couple of really clever methods to help us out. The two most popular are called the elbow method and the silhouette score. The elbow method is a really neat visual trick. Basically, we try a bunch of different Ks, say from 2 to 10 clusters. For each one, we calculate a score that tells us how tight the clusters are. Then we plot it. And what you see is that as you add more clusters, the score gets better and better, but eventually, it starts to level off. That point where it bends, the kink that looks like an elbow, that's usually a pretty good bet for the best K. It's the point of diminishing returns. The silhouette scores even better because it looks at both tightness and separation. It gives every single data point a score from -1 to +1. If a point gets a score close to +1, perfect. It's in the right place, far from other clusters. A score near 0 means it's kind of on the fence. And a negative score, that means it might actually belong in a different group altogether. We just pick the K that gives us the highest average score. Okay, mission accomplished. Well, almost. We've used our metrics, we've picked the perfect K, and the algorithm has sorted everything into groups. But right now, all we have is a bunch of data points with labels like Cluster 1 or Cluster 2. The next big step is to actually see them and figure out what they mean. But this is where we hit a massive wall. Our retail customer data isn't just two things, like age and spending. It could have dozens of dimensions: how often they buy, what categories they like, when they last visited. How on earth are you supposed to plot something with 50 dimensions on a flat computer screen? You just can't. This is where some truly incredible math comes into play. We use a technique called dimensionality reduction, and a really popular one for visualization is called TSNE. Don't worry about the long name. Its whole job is to take all that complicated high-dimensional data and squish it down into 2D or 3D in a really smart way. It works hard to make sure that points that were neighbors way up in 50 dimensions are still neighbors on our 2D plot. So before we use a tool like TSNE, this is what our data looks like if we try to just flatten it. It's a mess. A big, chaotic, overlapping jumble of dots. You can't see any groups, any patterns, nothing. It's all hidden in the complexity. And then, boom, after we run our data through TSNE, the fog just clears. Suddenly, these beautiful, distinct groups just pop out of the chaos. We can literally see the clusters that our algorithm found. This is just an incredibly powerful way to confirm that, yes, there's something real going on here. This is so cool. We can actually see the groups now. But the final piece of the puzzle, and maybe the most important one, is figuring out who these groups are. This is what we call cluster profiling. We're going to play detective and look inside each cluster to give it an identity. So, going back to our retail company, we might look inside our clusters and find something like this. Cluster 1, turns out they all have high incomes and spend a ton on wine. These are our VIPs. Cluster 2 is the opposite, lower income and they don't spend much. These are our budget shoppers. And Cluster 3 is everyone else, in the middle. See what we did? We went from abstract data to real human personas. And that is the payoff. This brings us right back to the beginning. Now that the company understands these different segments, they know exactly what to do. They can send exclusive offers to the VIPs, send special discounts to the budget shoppers, and create totally different campaigns for the occasional buyers. They can finally solve that business problem they started with. At the end of the day, clustering is so much more than just an algorithm. It's like a new lens for looking at the world. It gives us the power to find meaningful structure in almost any chaotic data set you can imagine. And that really leaves us with a huge question. Now that we have this ability to see the hidden patterns all around us, what are we going to do with it?